Hello AP Stat students, welcome to lesson 3.1 on scatter plots. Usually in class I start off by offering a big Halloween bowl of candies, and I ask the students to come up one at a time and grab as many candies as they can, and then to take their candies and count how many they got. So we would go about this for quite a while, and I would ask students, how can you predict then how many candies the next person will grab? Well, my students have a large diversity of ability to grab candy. First, competitive nature. Second, well, what are some other things that equate to being able to grab candies? So we go around the room and we think about, well, what's making one person grab a bunch of candies and other people just grab a few candies? So if I grab 6, but what if somebody else could handle this many? Okay, so let's see. 1, 2, 3, 4, 5, 6, 7, 8. How come that person could grab 8? So we start talking about hand size. So we say, okay, so let's take these two variables here. What is your hand span? So we go from 0 when we measure out on the little ruler here, and we say, oh, about 7 3/4. Okay, so this 7 3/4 hand span person can grab 8 candies. And then we keep measuring, and we say, okay, we think that the span of your hand, your ability to, reach a lot and grab around and have a lot more gripability for your candies is going to indicate how many candies you can grab. And so then we start making predictions like this. Now, predictions are going to go on a scatter plot then, on 2 axes, and we're going to say that hand span is going to come first, and that's going to predict how many candies you can grab. And we'd say that for people with small hands, that they can grab small amounts of candy, and for people with really large hands, that they can grab really large amounts of candy. So we would see a positive trend. Okay, so let's take that there and move on to this lesson. So why do we study relationships between 2 variables? We study relationships to make predictions, to explain phenomenon, and to maybe uncover a deeper story. So in Texas, some young girl realized that if she goes to the other side of San Antonio, that the supermarket has a lot more organic options. And she thought, what the heck? I want to buy organic. I want to eat right. And my supermarket, by me, of the same name, has less organic options than the one across town does. So what she found out too is that the mean income near her house was about $30,000, and the mean income on the other side of town is $120,000. So she thought, golly, they're putting the more expensive organic food for the wealthier clientele. Okay, and she thought that was a discrepancy, a disparity, and that's not fair, that they don't have access to good quality food. Okay, so that's why we study relationships between 2 variables, to make a story, to make to make a stand about an issue we feel strongly about. Okay. A response variable measures an outcome of a study. That's the second variable, so I put a little 2 there. That would be how many candies we grab. An explanatory variable may help explain or predict changes in a response. So the explanatory variable comes first. That's your X variable, and explanatory has the letter X in it. Okay, so explanatory variable would have been hand size, and response would have been how many candies we can grab. So explanatory kind of comes first, how big your hand is, and then response is how many candies. For example, different drug doses to treat illness. The explanatory is the drug dosage, and the response is the time to recover, or the quality of your recovery, or the effectiveness of the recovery itself. The only option for displaying a relationship between 2 quantitative variables is a scatter plot. That's 2 quantitative variables, okay? And these should be ordered, or what we call bivariate. So it would make sense to put the first variable paired with the second. So Joe's hand span and amount of candy he can grab and Becca's hand span and the amount of candies she can grab. Okay, and so on. It's right to put Joe's hand span with Joe's candies and Becca's hand span with Becca's candies. Okay, how do you know which variable to put on which axis of a scatter plot, and where do you start each axis? The explanatory variable always goes on the x-axis, the response on the y. If there is no clear explanatory response, and you just assign one to one of them and the other to the other. Does not have to start at 0, 0. In fact, it should not. You should be able to jump on the axes to right where you have minimum values of x and minimum values of y, so that we can see the scatter plot where kind of blown up and fit to match our graph space. And I try to always make it match kind of a square shape. Okay, x and y axes don't have to use the same scale either. One can count by ones and one can count by thousands. Okay? All right, what is the easiest way to lose points on the AP Stats exam? By not labeling and by not scaling both axes. Make sure you go crazy with all your tick marks, with all your numbers, okay? Track and field day. The table below shows data for 12 students in a statistics class. Each member of the class ran a 40-yard sprint, then did a long jump with a running start. Make a scatter plot of the relationship between sprint time in seconds and long jump distance in inches. So what we did is we took sprint time and long jump distance, and we figured that the more athletic people would probably be athletic all around. We figured that your faster sprint time people, so people with lower times because they finish the sprint sooner, okay, after just 5.5 or 6 seconds, that these people would also have a longer long jump because they're just simply more athletic, and maybe that speed helps them if they've got that running start for their long jump. Okay, and then their long jump distance. So I'm counting here by half seconds, and I'm counting here by 30 inches at a time. And that's perfect, okay? I should not start this axis as 0. I should start it at right around 50-ish, okay? All right, so there's my 60 right after the axis, okay? What 4 characteristics should you consider when interpreting a scatter plot? Folks, it's not enough to just give a plot, right? We have to then tell the story. We have to then say that the student in Texas is right, there's a discrepancy, this is a disgrace, okay? We have to be able to also get real geeky with what we see here. Is there a strong relationship with the grocery stores in Texas? Is there a strong relationship with your hand size and the amount of candies you can grab, or a strong relationship with the speed of your run and the distance you can jump? Okay? Or is it a weak relationship? So here we have a discussion on direction. What direction do you even have? Is it positive to the right, negative to the right, or neither positive nor negative? So positive direction in the scatter plot means it goes upward to the right. That means that as we read that x increases, y also increases, and we would always read it as x increases. We think of the x almost as a timeline, okay? And so we think that we read this left to right. So what is the graph doing as we go left to right? It's increasing, and as you go left to right, the graph is decreasing. Okay. The form. Is the shape linear, curved, or linear, is the shape linear, or is it curved / non-linear? Okay, don't let 1 or 2 points sway you, but what do you generally see for the whole trend? And you might have to cover up 1 or 2 naughty points that deviate. Here, linear. Here, curved. Strength. Is the association strong or weak, moderate or very? Okay. Strength is how closely the points follow the form. That is referring to the least squares regression line, because that's the form that we're most concerned with this chapter, all about the least squares regression line. So does it closely follow a linear pattern, or does it deviate by a lot, or something in between? So here we see a very strong linear association because the points are all seemingly perfectly lined up. Here we see a weak linear association. We do kind of see a linear pattern from bottom left to upper right, or upper left to bottom right. but we see a larger amount of cloud. Okay, so strong means they all closely follow linear form, and weak meaning they have some spread. Also be sure you can mention outliers, which are points that are outside the overall pattern, or clusters, and always mention context. So this is time spent on the strategy. Oh, okay. All right, so let's say that I gave a strategy type quiz, okay? And I gave it to 3 different groups of students: honors AP, regular, and special ed students. Let's say that the more time that students spent on the quiz within each group of ability, that the better they did. So the more time that my honors AP students spent on the quiz, the more time that my regular students, the more time that my special ed students spent on the quiz, the better they did. But in general, as I take more time, time alone seems like an indication of doing worse on the quiz, because as we see time tick forward, and we don't have anything scaled or labeled here or scaled here, but as we see time advance, we see the general trend that students seem to be doing worse. But that wouldn't be true that the more time that you spend on this strategy quiz, the worse you're going to do, because within each ability group, we see that the more time the honor students spent on it, the better they did. The more time the regular and the more time the special ed students did on it, the better they did. So it's important to mention these details and to really read it for the meaning of what it's actually telling you, okay? It is not saying that the more time you spend on the quiz, the worse you're going to do. Describe what you see in the track example. So let's go with these details: direction, form, strength, and outliers, and don't forget context. Okay, we see a negative, moderately strong linear relationship. I already covered 3 things, realize: direction, strength, and form. Okay, between long jump distance and 40-yard sprint. There's my context. One more thing: students who took longer to run 40 yards tend to have a shorter jumps. There are no clusters or outliers. There it is, the last part. Okay, the following scatter plot shows the amount of sodium in milligrams and amount of fat in grams in salads from McDonald's with no dressing. Describe the relationship between sodium and fat. Sodium, we realize, doesn't initially have much to do with fat. Sodium is kind of like salt. So how salty is your salad? How fatty is your salad? When we associate more sodium with coming along with fattier meats, then we see that once you start maybe adding more salty ingredients, that those unique salty ingredients are also high in fat ingredients. So it's not just that you're sprinkling salt on the salad and you're getting fat out of it. It's the fact that it's kind of a confounding, sodium's kind of a confounding variable linked with fatty foods. Okay, so there's a positive association between sodium and fat. Salads with more sodium tend to have more fat. There are 3 distinct salad clusters, possibly no chicken, grilled chicken, and fried chicken. Each cluster has a positive linear association. However, the overall pattern is nonlinear. It is curved. Okay, so notice that I talked about what the association is within each cluster. Okay, because we do see a linear association. However, my association is somewhat curved overall. Okay, the association is fairly strong and there are no apparent outliers. So even though I have a curved association, I can still talk about the strength of it, okay, in words by saying that it's strong. Okay, in this case, because neither fat nor sodium necessarily comes first, then either of these could have been on the x-axis. Okay, and we could have still talked about the relationship between fat and sodium. All right, to do this on your calculators, we should go to Stat, Edit, and type in data in this here, in your L1 and in your L2 for your X and for your Y data. Then we would do a couple more steps, but maybe it would make more sense for me to actually show you with a problem. Okay, so I'll save that for later. Now, just like two distributions can have the same shape and center with different spreads, two associations can have the same direction and form, but very different strengths. So these are both positive, they're both linear, so that's my direction, my form, but one is weak and one is strong. Okay, so let's talk about the strength of the relationship and actually quantify that. The correlation R measures the direction and strength of linear associations. It does not address the form, so alone my correlation will not tell me if the form is linear or is curved, but it will talk about the strength of the linear pattern. So even curved relationships you can get an R or a correlation value for even curved relationships. So don't take R alone to mean that the form is straight, okay? Because I can get an R value for any association, and many of forms will even result in a high R value. Okay, so here's just some R values to kind of get you used to what R is. So here's R value of 0. That means that there's no linear strength. Okay, here's an R value of negative 0.3. Possibly because of these few dots kind of over here in kind of the right half, lower right half, and then these few dots over here in the upper left half, and then it's trying to take those and try to kind of see a negative linear pattern that's just very weak. An R value of 0.5, that's exactly halfway to being strong, okay? And it's positive 0.5, so that means that it's going upward to the right. So R does reflect direction, where negative R values describe that there's a negative direction going on, and positive R values describe that there's a positive direction going on. R values very close to 0, like this one even, describe that there's really no linear strength present, and R values closer to 1 or negative 1 describe that there is a stronger or very strong linear relationship present. Okay. So realize that all the negative values come for the pattern going downward to the right, and all the positive values are associated with the pattern going upward to the right. What are some characteristics of the correlation? So R is always between negative 1 and 1. It's less than 0 for a negative association, and it's positive for positive associations. It is close to 0 for a weak linear association, but it's closer to 1 or negative 1 for a stronger linear association. R does not have a unit of measurement. So we don't say inches, we don't say standard deviations, we don't say anything about correlations, unit of measurement. R, or the correlation coefficient, does not make a distinction between x and y. Therefore, if you swap x and y, you get the same R. R does not change when we change the units of measurement, okay, because R uses standardized scores. So if we change from inches to feet or from minutes to seconds, and our x or y axis scaling changes, then this point is still so many standard deviations to the left of the x mean and below the y mean, and so it doesn't actually, with the R value overall will not actually change because it's based on z-scores of each of the points. Okay, then what we would do is we would have an applet on the computer, pull up a whole bunch of different scatter plots, and you in the class would go around and guess, and we would play like a little March Madness kind of brackets of who's the best at guessing the correlation. Which association is more linear? One with R equals 0.5, one with R equals 0.9. You actually cannot determine the form of a relationship using only correlation, using only an R value. R is a supplement for a graph, it is not a replacement. So R can be 0.97 for something clearly curved, but it can be 0.5 for something a lot more linear. Okay, y equals x squared. Realize that this is a common graph. It's a graph of a parabola, but so we would only be viewing the right half of it probably. has a correlation of 0.97. That's huge. That's almost 1. Okay, for all x values from 1 to 10. So yeah, we're only viewing the right-hand side. And oh my gosh, that's crazy, right? So be careful. This is clearly a curved pattern. That's a parabola. Okay, that's a parent distribution of this is a parent curve of a parabola. Okay, and wow. So don't jump to thinking that you can just look at an R value and therefore conclude the graph's shape. Show linear association with a weak R. Okay, that's right here. Also illustrate a parabolic form of a correlated zero. Okay, is correlation a resistant measure of strength? Oh, yeah, here we go. Okay, I wanted to show you these two plots here. So the scatter plot here can have a R value of 0. Okay, and this can also have an R value of 0. So 0 alone doesn't necessarily mean that there's absolutely no pattern in the plot. Okay, if we see a really strong parabolic relationship, then that's awesome. It's just that a line does not model this relationship. Okay, but a curve perfectly models this relationship, and that's substantial. That's excellent, okay? It will still give you an R of 0, or very close to 0 though, because R only measures how well the points line up on a line. Okay, so this might have an R value of 0, that might have an R value of 0. It doesn't mean that there's not some pattern going on, although maybe it does. It means that there's no pattern going on, but essentially it just means there's no linear pattern going on. Okay, all right. Is correlation a resistant measure of strength? Correlation is not a resistant measure of strength. Extreme values do change the correlation. Okay, an outlier in the pattern makes R close to the absolute value of 1, so 1 or negative 1, but an outlier out of the pattern makes R closer to 0. So those are your answers to, is correlation a resistant measure of strength? Okay. Do you need to know the formula for correlation? It is on the formula sheet. Relying on your calculator to find R is perfect. Understanding the formula is important though, so here it is. It's the summation of the product of all the z-scores, all divided by n minus 1. So therefore, if you have a low to the left point on a scatter plot, like here, then it's going to have a negative z-score for x and a negative z-score for y, and then two negatives are going to multiply to a positive. Oh, here, I start describing it here. Let me just keep up with it here. Here are the data in lengths in centimeters of a femur, a leg bone, and the humerus, a bone in the upper arm, for the 5 specimens of Archaeopteryx, I don't know, that preserve both bones. Okay, so here's different femur measurements. Here's different humerus measurements. Here I found the mean and the standard deviation of femurs. Here I found the mean and standard deviation for humerus. So what I did for each of these points then is I did observation minus the mean divided by standard deviation to turn each of these into a z-score. And I got 2 negative z-scores, 1 very close to 0, and 2 positive z-scores. Same thing for these down here. When I just straight plot them, my femurs go from about 38 to 74, so I went like 35 to 85, and then, I went from 35 to 75, and then my humerus went from about 40 to 84, so I could go from like 40 to 85 or 35 to 85. Anyway, so here are my 5 bone amounts, 1, 2, 3, 4, 5. Pretty linear, okay? All right, so make a scatter plot and describe what you see. We see a very strong positive linear relationship between the femur length and the humerus length for this type of specimen. Okay, there are no outliers, I would just say. All right, then next, when I take this, oh, that's right. When I take the mean, 58.2, and I draw a line for it, and I take the mean 66 and I draw a line for it, then if I count out in standard deviation units of 13.2 from here, then right above 58 is like 72-ish. So then I make a dotted line right there, and below 58 minus 13 is around 45, so I make a dotted line there. And I did the same thing for the y coordinates. I took the mean at 66 and I added about 16 to it, and I subtracted about 16 from it. So now I have the means cross, and I have standard deviations of -1 and 1 and -1 and 1. Okay. All right. So next what I saw is that these observations, what they do, they gave me these products then as I worked through the z-score times the z-score. So here's the numerator, z-score times z-score, and then the two z-scores timesing each other for the next ordered pairs of the next specimens, femur and humerus, and then the next z-scores for the next specimens, femur and humerus. And what we see is that for this specimen that has a smaller than average femur, they also had a smaller than average humerus. And then here's a femur and humerus z-score, and here's a femur and humerus, and a femur and humerus, and a femur and humerus. So here's all the components of that then. For values that varied quite a bit from the mean, like this one that was more than one standard deviation smaller than the mean femur, and for more than one standard deviation smaller than the mean humerus, then those values resulted in a decently large product. These two values that were a little bit closer to the mean, only half a standard deviation small and a fifth of a standard deviation small, resulted in a smaller component. And then these two also quite small. These two a little bit larger but quite small. And then these two a little bit larger component. So what makes up the largest components of this? The points that are pretty far away in standard deviation units. Okay, what makes up very small components of the R value? Points that are really close to the mean. Okay, so what makes R large? Actually, by having points pretty far out, like let's say even outliers that are in the linear pattern, okay? Because they're going to have extreme z values, either negatives or positives, okay? They're more than one standard deviation to the right of for the femur and for the humerus, okay? Those are going to make larger components that are going to make this overall value larger, okay? And values that are close to the mean are not going to affect the R value much at all. Okay. What are some additional facts about correlation? Correlation does not describe the strength of a curved relationship. So if you have a perfectly curved data set, you might have a large R just because they might sort of line up too, okay? But correlation will not be a high or a low value for a perfectly curved relationship because the points are curved. It would only be high or low, close to 1 or close to -1, because the points ironically also line up decently well. So what this is showing you back here is that for this data set, that maybe the least squares line would cross through like this. So none of these points are all too far from the line. So that might have a high R value. Okay, so curved relationships might or might not have a high R value. It has more to do with how close those points are to a line though. Okay. Okay, I think that's good enough for today. All right. Oh yeah, over here is important too. One more thing. Okay, so I just kind of detailed out your average kind of way of describing weak or strong for a correlation. For the strength of linear relationship. So if points are pretty close to around -0.2 to 0 to 0.2, we would describe the relationship as very weak. But if the value is somewhere between 0.2 to 0.5, or negative 0.2 to negative 0.5, we would just describe the relationship as weak. And if it's from 0.5 to 0.7-ish, then we describe it as moderately weak or moderately strong. I think I would go moderately strong. If it's from 0.7 to 0.9, I would call it strong. And if it's 0.9 or higher, I would say that it's a very strong linear relationship. Okay, thank you very much for joining.